All right, now we've done a little bit of EDA or exploratory data analysis. We're going to do one more step, and that is building a correlation matrix. You might be thinking, what is a correlation matrix? In layman's terms, it's a big table of numbers telling us how each independent variable is related to each other, aka these columns here, how do they interact with each other? Are they a positive correlation or are they a negative correlation? Now, let's not talk about it for much longer because we want to see it. We want to see what is happening. So let's go make a correlation matrix. And to do so, we can use df.core. If we hit Shift Tab here, compute pairwise correlation of columns, excluding NA/null values. Well, pairwise correlation, that's just basically saying compare each of these columns to each other. Well, let's see it in action. If you're looking at this for the first time, quite confusing because there's a lot of numbers going on here. Okay, you can see the columns are on the rows as well as the columns. And the diagonal here is 1, 1, 1, 1. There's a lot of decimals, and some are negative and some are positive. What we might do though, instead of staring at this and exploring it for a little bit, we might make this a little bit more visual. So let's make our correlation matrix a little prettier. And we're going to do that using Seaborn's heat map. So we'll set it up in a variable. So core matrix equals df.core. Wonderful. And then we'll set up a figure and an ax using, plt.subplots. That's it. Fig size. I kind of know the fig size because I've seen this plot before. So I want it to be 15 width and height. And then we're going to go ax equals sns.heatmap. Would help if I typed map. And then we're going to pass it core matrix. And we want to annotate it, so we'll set a not to equal true. And we also want a line width. Line widths? Yeah, I believe that's it, of 0.5. And then what else do we need? There was a couple more things. Format equals, we only want 2 decimal places. So see here, these are like 6. So two's going to be enough for us. And then CMap, to give it some nice colors, we'll go yellow, green, blue. Wonderful. Let's check it out. Invalid syntax. Oh, forgot the comma here. Classic. Wonderful. Okay, so what is this showing us? We've got some cutoff things here. That's that pesky matplotlib 3.1.1 error. But that's all right, we can fix it. So we might go bottom. You might not see that if you're using a later version of matplotlib than what I'm using at the moment. We need to adjust the y-axis limitations. So we'll go get ylim. Wonderful. And then we're going to go ax.setYlim. That's it. That's how we change it. We want to move the bottom up and we want to move the top down. Does that make sense? So bottom plus 0.5 and top minus 0.5. Does this work? Wonderful. That's looking a little bit better. It's not cut off. And this little adjustment here, this is from the research that I found by just searching for it. So matplotlib, Seaborn, first. I think that my history might have had it there. Matplotlib, there we go. First and last row cut off. That's an example of searching for your problem when you have it, right? When you run into an issue, it's just about trying to figure it out. So they've got a similar problem to what we just had, cut off. And then come down here, you can find this is the lines of code that I'm using here. And in fact, they're making a correlation matrix as well. Beautiful. Yeah, unfortunately, Matplotlib 3.1.1 broke Seaborn heat maps. But that's all right. We've got our heat map. We've got our correlation matrix. Again, this is just the same version of this. A more visual format. I look at this and I understand this one a lot better than I do this one. So what is actually going on here? Well, we can see on the diagonal, we've got a lot of 1 values. But what this means, the diagonal is, we might zoom out 1 tick so we can see. The diagonal, this is giving a perfect correlation, which means the age column is exactly equal to the age column, which makes a whole bunch of sense, right? And the sex column is completely equal to the sex column, and so on and so on and so on, all the way down the diagonal here. But then we have a lot of other actually, little cells here. We can see on the side, we got 0 up to 1. And some of them are positive, like this one here, and some of them are negative. We just compared chest pain type, which was CP, to our target. Let's investigate that. What's the correlation here? We got CP, it's got a positive correlation. So 0.43, remember the maximum value is 1. But this is telling us how chest pain is related to the target column. Well, if we're looking at this, and we did some research on a correlation matrix, I'm going to tell you because I've done this research myself. A higher positive value means a potential positive correlation. And a higher negative value means a potential negative correlation, or a decrease. What this is saying is as CP goes up, the target value also increases. Now, does that make sense? If we come up here, so if we look at this plot that we did before, so as CP goes up, the target value also increases. So remember our target value is 0 or 1, 0 for no disease, 1 for disease. Now, we're most interested here in the correlation because if you looked at this, no disease is highest at 0. So that means no disease, the target is 0, and chest pain type is also 0. Okay, so according to our correlation matrix, as CP goes up, because it's a positive correlation, the target value should also go up. So let's investigate. Disease, this is the 1 value, and this is 0. So blue is 1. Salmon is 0. Salmon, what a beautiful color. As our chest pain type goes up, 0, 1, 2, 3, does the blue column for 1 of target value go up? If we look here, it does go up slightly, and this drops off dramatically. And then it goes up here. It goes down here, but the ratio of disease to no disease is still much higher. So that's where the positive correlation comes from. It comes from chest pain type increasing, or our CP column. As that increases, our target column, meaning disease or no disease, also increases. So that's a positive correlation. That's why it's positive here. Now, let's have a look at one of the negative columns. So we've got a negative correlation here. It's about the same ratio, but just in the negative way. That means, if we look here, Xang, we'll check our data dictionary for that in a second. As Xang goes down, so should the target value. Let's not take this correlation matrix word for it. Let's reproduce this plot, except using the Xang column. But before we do that, we might jump up here. What is Xang? Exercise-induced angina. Now, if you're wondering what angina is, we checked out that before. A condition marked by severe pain in the chest. So this means that if you exercise, do you get heart pain? And let's have a look. Exercise-induced angina, 1 equals yes, 0 equals no. So do you get heart pain when you exercise? If you do, that's a 1, and if you don't, that's a 0. There's a negative correlation according to our correlation matrix. I'm saying correlation a lot, I know. So Xang, compared to the target value, do they have disease or not, is negatively correlated. That means as Xang goes down, the target should also go down. Now there's only 2 values here for each of these, so this is actually a pretty straightforward example. So if we think about this, based off what you've heard about in terms of heart disease, if someone was telling you that when they exercise, they get chest pain, so they would have 1, would you predict closer to someone having heart disease or not? If they had exercise-induced chest pain, what would you be more inclined? Do they have heart disease or they don't? Well, for me, I would be more inclined to say, well, based off the rest of the data, if they're getting exercise-induced chest pain, there could be something going on with their heart, right? They could be heart disease. So this is where there's a negative correlation. This is where the negative correlation comes into play. Let's go down here, back to our correlation matrix. So there's a negative correlation of negative 0.44. So that means as Xang goes down, the target value goes down. Based off what the core function is seeing in our data, exercise-induced angina, when I compare that column to the target column, I'm noticing that when Xang is lower, so is the target column. Based off what we're looking here, and remember, it's only a 0.44 correlation. It's not a perfect one, like -1 correlation. But just, it's trending towards, if someone didn't have chest pain, so didn't have exercise-induced angina, the trend is negative, so it's trending towards them not having heart disease. Does that make sense? And you could go through all of these values. So this is pretty flat. Like, this is almost basically zero. There's no correlation between FBS and the target. What's our data dictionary telling us? FBS. So fasting blood sugar. So this is saying, is the fasting blood sugar above 120 milligrams per deciliter? I believe that might be deciliter. 1 equals true, 0 equals false. So that's basically saying they're perfectly even. There's no real positive or negative correlation. It is what it is. And so that's the kind of insight that you can start to form with this correlation matrix. And that's the kind of insight that we want to sort of figure out on our own if we weren't medical experts and we could only work with the data that we have. This is the purpose of EDA. This is the purpose of what we've gone through here, comparing different variables, looking at the distribution, comparing more different variables here. And this process, we could keep going with this, right? We could keep going until we really, really understand the data. But what we want to do next is model-driven EDA. So what that means is building a machine learning model to derive insights of how these independent variables here contribute to the target variable. Now, correlation matrix is one of them, but we're more interested in trying to predict for the future. The correlation matrix only deals with the data that we have. We're more interested in building a machine learning model that has predictive power based on the data that we have to predict on things in the future. So that's what we're going to look at next. If you're a little bit stuck here of what the correlation matrix is, don't worry. It's a pretty in-depth concept to understand, but where you can probably go next is by just searching, what is a correlation matrix? So you go here, what is a correlation matrix? You could go to this first link. A correlation matrix is a table showing correlation coefficients between variables. Well, that sounds like a good resource. Start to read up on a little bit more. Hey, that looks a little bit like the graph that we made. But we've covered most of the crux of a correlation matrix. It's really just going, okay, looking at two variables and going, is the relationship positive, aka as one increases, so does the other? Or is the relationship negative? As one decreases, so does the other. But let's have a look at our workflow, see where we're up to. We've been through some data analysis. Now's time to get onto the machine learning in the modeling section. Let's see where we're up to here. If we look at our new project workflow, we've covered this. We've looked at some exploratory data analysis using NumPy, Pandas, and Matplotlib. Now's time to get into the machine learning part of things using scikit-learn. We'll start to test our little theories about what we found out in the exploratory data analysis. We'll start to see, does our machine learning model agree with what we found here, just exploring the data on our own?